Okie dokie. Welcome to the next video here in finding absolute extrema. So figuring out where the highest and lowest point of the graph is without looking at the graph this time because A, B, C, and D are just functions given in terms of equations. What we're going to check is, do all of these qualify for the extreme value theorem? And so if I look at the first function, this is a quadratic function. Quadratic functions are parabolas, and parabolas are always continuous. And this is a closed interval. So yes, I can use the extreme value theorem, and I know, that I will find a highest and lowest, a highest and lowest point, an extreme value, an extreme maximum, and extreme minimum value. When I look at the second function, at first, this function looks like it might be difficult, except remember, we're just dividing by 2. So this is the same thing as 1/2 times x squared minus 1 quantity squared. Well, that means in reality, if we were to multiply this out, and I'm not asking you to do that, but if we were to multiply this out, this would give me a quartic or fourth degree polynomial, and that is also continuous, and this is a closed interval, so the extreme value theorem is going to help us there. Okay. When I come over here, now I might run into some problems because I have a rational function, a function that's written as a fraction. And there is an issue. There's an issue at x equals -3, there's a vertical asymptote, right? Because that would make the bottom equal to 0, the top not equal to 0. However, the closed interval where they want me to evaluate the absolute extrema does not include -3. So therefore, the problem where the problem exists is not in the window that we're working with, so I can use the extreme value theorem. And then finally, this function, I have the sine function minus the linear function, both of which are continuous. So when I take the difference of them on the interval between 0 and pi, the extreme value theorem will work. So for all of these four, the extreme value theorem will be a an idea that we can use to guarantee that we're going to get an absolute max and an absolute min. Great. But now we're going to go through the process of finding what is the actual absolute max and min. And I'm actually going to do B and C. I feel like A might be a little bit too easy. So let's look at B. If you remember, and if you don't remember, I guess I should say, if you don't remember the steps, we said we're going to need to find critical values. So we're going to find the derivative and see where the derivative is equal to 0 or undefined. We're going to create a table of values that include those critical x values and the endpoint values. And then we're going to find the absolute extrema by plugging in x values into the original function equation. And then we'll see which one is the biggest value, the highest value, and which was the lowest value, because they're going to be designated the absolute mins and maxes. So first thing I need to do is find the derivative. Could I use the quotient rule? I certainly could. I have a top and I have a bottom. However, when I rewrote it over here, this is a chain rule. And so I can take the derivative by multiplying 2 times 1/2, which is 1, with the inside still in it, to the 2 minus 1 power, which is 1, times the derivative of the inside, which is 2x. So now, if I rewrite it just slightly here, I'm going to set the derivative equal to 0. What are the x values that would make this equal to 0? Well, x equals 0 because that would make this factor equal to 0, and then 0 times anything is 0. Another one would be 1 because 1 squared is 1 minus 1 is 0 times anything, it would be 0. And the other one is -1 because -1 squared is 1 minus 1, that's 0 times anything would be 0. So there are 3 critical values. I'm going to write it out. 3 critical values. So that was step 1, find the critical values. Step 2, make a table of not only the critical values, but also the endpoints. So I'm going to put them in order, not that you have to, but I will put them in order. So this is an endpoint, this is an endpoint, and then these 3 are the critical values. And what we're going to look for are g values. In other words, I'm going to take this number and not put it into the derivative, I'm going to put it into the original function. And so I put it into the original function, and I'm going to use this version of it. So 1/2 times negative 3 squared, that's 9 minus 1, and then squared. So that would be 9 minus 1 is 8. 8 squared is 64, and half of 64 is 32. And then I'm going to do the same thing with the next one. Negative 1 squared, that would be 1 minus 1 and then squared. So that's going to be 0. So then I just get 0. 1/2 times 0 squared, which is 0, minus 1 squared. I believe that's going to be 1/2. 1/2 times 1 squared minus 1 squared. That's going to be 0 again. And then 1/2 times 2 squared, that's 4 minus 1, and then everything squared. I believe that's 3 squared, that's 9, and then half of 9 would be 4.5. So what did I do? I took the endpoints, these two numbers, and I took the critical values, these three numbers, all of them x values, and I substituted them substituted them into the function in order to get the y values, the original function, to get the y values, because I know that absolute maxes and mins are based off of the original function y values. So the biggest one would be this. So I can say the absolute max is 32 at x equals negative 1. And I can say that the lowest y value is actually 0. So the absolute minimum is 0, and that happens at x equals negative 1 and x equals positive 1. So make sure to show that you've evaluated not only the endpoints and the critical, not only the endpoints, but the critical points and the endpoints into the original function to figure out which one it is. A lot of students, they do this part and then they write this because they did something in their head or something. They need to see that you actually evaluated them. Do you have to show all of this work? No, you can just say negative 3, but your labels will come in handy because they know that you evaluated this x value into the g function and you got 32. Right? So you don't have to show all the work, but make sure you label your table, make sure you write the values, and then you can see the biggest value wins the award for absolute max, the smallest y value wins the award for absolute min, and we found our extreme values that we were looking for. So again, recap. Step 1, find the critical values. Take the derivative, set it equal to 0, find where it's undefined. Once you have those values, make a table with those values and the endpoints, and you're going to evaluate not the derivative, but the original function, and then whoever wins the biggest one is the absolute max, smallest one is the absolute min. We're going to do the same thing with letter C. For letter C, we, again, have a choice. We're going to find the derivative. We could use the quotient rule. Some students like to rewrite this into x plus 3 to the negative 1, and then they have to do a product rule. For me, it's really 6 of one, half dozen of the other is the same thing. So I'm just going to do the quotient rule. Take the derivative of the top times the bottom minus take the derivative of the bottom times the top all over the bottom squared. That's the quotient rule. Let's simplify. So that's going to be 2x squared plus 6x minus x squared. All of that over x plus 3. So I want to know where this is equal to 0, and I also want to know where it's undefined. Well, I already know when it's undefined, it's going to be at negative 3. However, negative 3 is not in our window, so we don't need to worry about it, right? So there's a critical point. There's a critical value at x equals negative 3 because that's going to make the derivative undefined because it's going to get a 0 on the bottom. However, we don't worry about it because not in the interval, so we can scratch it out. But let's keep going. Let's simplify this top part. I think I get x squared plus 6x, x plus 3 squared. Okay, so now I need to figure out what makes the top equal to 0, right? What makes the bottom equal to 0 is going to be the undefined. What makes the numerator equal to 0 is going to be what makes the whole fraction equal to 0. So I'm going to set the numerator equal to 0. And I think I can factor out an x, which is going to make it easier to see that this is a critical value and this is a critical value. However, once again, -6 not in the interval. So even though this is a critical value and this is a critical value, I don't need to worry about those. The only one I need to check is 0 because 0 is in that interval, as well as the endpoints. So I go to the next part and I say, here are my x values, -2 because it's an endpoint, 0 because it's a critical point, and 1 because it's an endpoint. And we're looking for h values, the original function of h. So I'm going to take this -2 and substitute it into the original function. So -2 squared, that's 4 over -2 plus 3, that's +1, so that's 4. 0 squared, that's 0, divided by 0 plus 3 is 3, and that's 0. And 1 squared is 1, divided by 1 plus 3, that's 4, that's 1/4. Well, I think I can see that the absolute max is 4, and that happens at x equals -2. And I can see the absolute minimum is 0, and that happens at x equals 0. Well, I need to identify these two critical values. I do need to evaluate them. But when I check them, when I check them on my table over here, I don't need to include them because they're not in the interval that we're talking about. But they still want you to find them. You're just not going to necessarily need to check these over here. But we found the absolute max and the absolute min using equations. On this last video, we'll look at some graphs. We'll use the extreme value theorem and the process for finding absolute maximums and minimums in order to figure those out.